Hello students, grade 11 students, A level. Today we are going to continue our chapter arenes or benzene. There are two discussions today. It is in 25.3. The first about combustion and then the second electrophilic substitution in benzene. Benzene or methylbenzene, they react with oxygen just like the other organic chemistry. Organic molecules, they react with oxygen to undergo combustion. There are two types of combustion, which is called complete combustion and then also incomplete combustion. Complete combustion will produce carbon dioxide and water, while the incomplete combustion will produce carbon and water. And then the difference between benzene with other organic molecule in terms of combustion, there are two differences. The first, benzene, the reaction is less exothermic. It does not mean it is endothermic. It is still exothermic. It produces heat energy, but the heat energy produced is less than the other organic molecules. And then the second, it requires high amount of activation energy. Why? Because the stability of the 6 delocalized pi electrons. Last week we discussed already about the stability of the pi electrons. This one, it means that the electron, the double bond, can rotate within the structure. And then now the second is electrophilic substitution in benzene. In similar way to the pi bond in alkenes, the delocalized bond in benzene is an area of high electron density. So the pi bond, double bond, has high area of electron density. But the difference is in benzene there are 6 carbon atoms and there are only 3 double bonds. And then these 3 double bonds, the location of the double bond is always rotating. So the pi electron is delocalized. And then because of the extra stability of the delocalized electron, however, the species that react with benzene have to be much more powerful electrophiles than those that react with alkenes. We know that in order to differentiate alkenes from alkanes, we have to use bromine water. Alkenes will dechlorize bromine water because of the high electron density of the alkene that push the electron in the bromine, that creates the bromine, these 2 bromine. The electron of this bromine is taken by this bromine. That makes this bromine is becoming electrophile or positive. Because this carbon open the electron and then it given the electron to this bromine pushing, that makes this bromine attached to this carbon. It becomes this structure. And then after that there is a nucleophile Br minus. So this one that makes the difference between alkene and benzene. In major difference between benzene and alkenes, what happens after the electrophile attack the pi bond. In alkenes, an anion acts on. So it means this one. This anion or nucleophile goes to here. Why? Because this one is positive. What does it mean positive? It lacks of electron. It needs to gain electron to make itself stable. Bromine ion, which is nucleophile, has extra electron. So this one to the dative covalent bond to this bromine that makes this structure. But in benzene, the carbocation intermediate loses a proton. So as to reform the ring of pi electron, this demonstrates how stable the localized system is. In benzene structure, this one dative covalent bond. So the bromine electrophile gains electron from the benzene, and then that makes the structure, this one is open, it's become carbocation. Now this and then this one, there is a 2 electron, and then this 1 electron goes inside to reform the double bond again. That makes it produces hydrogen with less of electron. This is called as the intermediate reaction. So in A level, they want you to draw all this, how the bromine at the substitution of bromine into the benzene. Next, let's continue. Alkenes react by electrophilic addition. Arenes or benzene reacts with electrophilic substitution. Please do not mind with the name of arenes and benzene. They refer to the same molecular structure. And then bromination. Benzene will react with non-aqueous bromine on warming in the presence of anhydrous aluminum chloride or aluminum bromide or iron chloride or even just iron metal. So this one is called as the reactant. This one are the catalyst. You may choose one of these catalysts. The condition is warm. In latter case, the initial reaction between iron and bromine provides iron 3 bromide catalyst. So the bromine, this one, has to be non-aqueous. So meaning it is molten. So this one, it creates this catalyst. Anhydrous aluminum or iron halide contain electron deficient atoms, so they need 1 electron. They can react with bromine molecule to accept 1 lone pair of electron on bromine. So this one, there is a bromine molecule, and this bromine molecule, there is an electron. Electron from where? From these 2 bromine shares 2 electron in the middle, and then this electron from here taken by this bromine. That makes this bromine has an excess of electron. This one will make dative covalent bond with this aluminum bromide or iron 3 bromide, and then that makes this one aluminum. There are 4 bromine around it. We know that aluminum by default, there are 3 electrons only in the outermost shell, but there is dative covalent bond that makes like this. And then after that the electron of the bromine is taken, and then there is this one, an electrophile, and this structure. And then this electrophile this electrophile react with the benzene. The bromine cation that is formed is powerful electrophile. Why? Because of the presence of aluminum bromide. So it becomes attracted to the pi bond of benzene. It eventually breaks the ring of electrons and forms a sigma bond to one of the carbon atoms in the ring. So this one form that covalent bond, and then bromine with this carbon, it will form sigma bond, and then two of the 6 pi electrons are used to form the dative bond to the bromine atom. The other 4 pi electrons are spread over the remaining 5 carbon atoms in the ring. The 5 center the localized orbital. So it means this is still containing delocalized, but only within this 5 carbon atom, while the 6th carbon atom undergo substitution reaction. So this one. The distribution of the 4 electrons is not even. The distribution of the 4 pi electron is not even. They are associated with more carbon atoms 3 and 5 rather than atoms 2, 4, and 6. The positive charge is therefore distributed over 2, 4, and 6. This is the best represented by the following classical mesomers. So this one, it will form like this. This is it forms positive, and then this electron goes here. So, and then it will rotate. This one, it shows that the electron is not stable. It can rotate. And then we shall return to the feature in the intermediate carbocation effect, page 427 later on. The intermediate carbocation loses proton and loses a proton to reform the sextet of the pi electrons. This one, the hydrogen, has electron. This electron goes here, and then the benzene loses the hydrogen atom because benzene, we know that benzene cannot undergo addition reaction. It only can undergo substitution reaction. The final stage regenerates the catalyst by the reaction between the proton formed in step 3 with the aluminum bromide ion formed in step this one. So H plus, and then there is AlBr4 negative. It forms HBr and aluminum bromide again. We know that from this that aluminum bromide is a catalyst. Why? Because the condition before and after the reaction the same. And then further substitution can occur with excess of bromine to form dibromobenzene, even with tribromobenzene. For the reaction of bromobenzene, later we are going to see in section 25.4. So today we are discussing only 25.4. If you have any question or any queries, please write in Google Classroom, and I will have online class today.